Okay, so I'm just gonna. You can just admit all. I'm gonna go do this meeting, then I'll come back. Just kind
Oh,
of.
there's some changes for master sharing.
Yeah, so you have to log in to Zoom from your computer. Yeah, and then, yeah, multiple, yeah.
One.
Oh, yeah,
Okay, so
okay. And then, yeah. Thank you all. For an audio. Just click this. Yeah, and then you're going to use that mic.
Okay.
And then you'll share through there, and it'll show up.
Okay.
I'll be back in like this meeting.
Okay.
And then I don't know if there's Mri coming later in the day. It looks like he said.
Yeah.
He said something.
He said, "Oh, good afternoon."
Oh, great. Okay, so. Oh,
Okay.
oh, here.
I'll listen.
Okay, what is it? Whoops. What happened? What did I do? I'm trying to let them in.
No?
There.
Oh, okay.
Okay, yeah, so you just. All right, I'll be back in a little bit.
Okay. Thanks.
I'll leave this door open for now. All people come in.
All right, we're gonna let people trickle in here. There are some couple scripts inside of the Google Doc. And if you did not do that Excel tutorial, which you didn't need to, there is a new data set that has been completely analyzed. So you can download that for this afternoon. I recommend doing that right after this meeting so you don't slow down your computer right now. Can people hear me on Zoom? It should be.
Yes.
Yeah, okay. All right, while we're waiting, I guess you can just open up FXL for now. You just type that into your terminal. Start in just a bit. So if you just type FXL into your terminal, you should get the GUI to open up. We will be using this for the second session. Dr. Martin Monti will be here to lead everyone to the tutorial from Andy's Brain Book. You did not need to have done it though. If you did not do it, download. There's a new link in the Google Doc. You guys all have the link for the Google Doc, right? Okay. Link in the Google Doc, so you can download the data set that has been already analyzed. And then I also put in a couple of new scripts inside of this little folder right here. There's just 2 scripts in there. You can just download those 2. Okay. Is everyone able to open up Excel? Their computer?
I was having trouble like downloading the FSO, but it kind of for like a version of the Mac.
Oh, do you have the newest version?
Yeah,
Yeah, it's a problem. You're gonna have to try and get access to your lab or something. So some people have been having a problem with the newest version of Mac and FSL, and this is a constant problem in neuroimaging. So you're gonna find a lot of people here are anti-update. A lot of us run a lot of the old versions simply for this reason. Whenever a new operating system or update comes out, all the packages have to sort of react to it and fix their codes. So, you know, unfortunately, there's nothing you can do about it. Let's just try to find a different way to access it. Or if you get access to Hoffman, then you won't need to worry about your computer configuration or things like that. Anybody else having any other type of problems? FSL? Anybody on the chat? Okay, so if you do have FSL and you open it up here, let's just go ahead and open up FSL eyes. That's what we're going to use a little bit later on. We're not going to go into it right now, but in just a little bit. But you should be able to bring up this GUI here. And we're gonna look at some brain images in just a bit. Oh, wait, what's happening here? Okay, my computer does not like this. Oh, there we go. Okay, so you can just get FSL eyes open. I'm gonna start with a short PowerPoint about what we're gonna be looking at today and some conceptual things that you'll need to know for the later session. So just really short on MRI acquisition basics. It's important to understand how we get these signals in order to understand some of the possible artifacts that are involved in acquiring these signals. Later on today, we're going to do the task fMRI activation. That's Andy's brain book tutorial. This is different from resting state correlations, which we are going to do in this first session today. And I'll explain the difference in just a bit. And then specifically within this resting state area, we're going to start looking at how to extract essentially a brain parcellation. So breaking up the brain into 400, 300 areas instead of 90,000 voxels. Okay, so this allows us to reduce the data. And essentially what we look at are correlation matrices, where we look at basically the functional connectivity structure of the brain. So on average, what do these connections look like during this resting state scan? Okay. So first, MRI basics. We have the current MRI signal, and basically, again, you're in this giant magnet. It's lining up all of the hydrogen atoms in the water molecules in your body one way. It's going to shoot a pulse. It's going to, when the RF pulse is applied, some of the atoms are going to spin the other way, and basically measuring what they call the precession or the frequency which these atoms rotate back into place, depending on where you measure it. You're essentially going to get a resonant signal. So using a giant magnet to get the resonant frequency of these atoms, and that produces an image. So magnetic resonance imaging. And basically, this image here is just a bunch of numbers plotting out the way these resonant frequencies change according to tissue type. So different tissue types give off different resonant frequencies, and this is basically the image that you're seeing here. And tuning, or not tuning, but how you say it, programming different ways to measure this on different types of tissue, you can get, guess what I talked about? You can get different types of images. Today, we're going to be going over two main types, or not two main types, I should say. We're going to be going over functional measures, but essentially what happens is you can get structural MRI, and that's just programming the scanner to look at different aspects, again, of these resonant frequencies. And if you open up your FSL eyes, and then if you go to some of the files, so let's go FSL eyes, let's see, overlay, or let's do actually this is easier. File, add standard. So if you go file, add standard here, you should get a bunch of brains popping up here from the FSL library. And let's go ahead and look for MNI 152 2mm brain. That guy right there, and open that up. So this is a structural image, an average structural image of some adult brains. It's named after the institute where they got it from, MNI, Montreal Neurological Institute or something. But basically, this is sort of the standard template that most people use when they are looking at group averages or whatnot. So this is a structural image. What you can do is click around in it and you see there are different values. So if you look here, there's going to be different values as you click around in the brain. And that's basically how you get these structural images here. Even though this is averaged over a lot of people, it's the same thing on a single subject. So if you click around again, that's what those values are. Essentially just getting those frequencies off of the scanner. And it's going to create for us a picture of the tissue types, essentially. Tuning the scanner a different way, we're going to look at blood flow instead of sort of tissue type. So tuning in the scanner another way, we're going to look at blood flow. And what happens is when you see these blobs, these are blood flow patterns overlaid on top of the structural image here. So that's why typically when they acquire things or acquire scans from a subject, they're going to acquire both the structural and the functional. And the reason, we'll probably go into this later, is that the structural is used to help sort of stretch or shrink these brains into a standard template. Okay, but the functional images, you can open those if you go to overlay, oh, let's see, file, add from directory, and then let's go into the data from Andy's brain book. Let's see. So if you have your data from Andy's brain book somewhere, or actually, you know what, go into this fun, the data you downloaded, so this fun image normalized. And we have 2 subjects in there. Oh, what is it? Oh, I'm sorry, it's not overlay, it's add from file. Let's see, that's the one. Oops. Yeah, so add from file and then choose one of these rest masked guys here. And then that's going to be a functional image. So you can look at the viewer here and you can turn off the structural image. So it's this little eye, turn off the functional image, little eye there. And you're going to notice right off the bat that the functional image has much worse spatial resolution. And the reason again for that is it's tuned to be sensitive to blood flow rather than tissue type, or oxygenated blood, I should say. And another thing you'll notice here is that if you just look at the structural brain and you go to these volumes, there's no volumes. So it's just one image. When we acquire a structural image, it takes a while. And basically you're just getting one image of the tissue types in your brain. A functional scan is different, and we'll talk about this in just a bit. So if you look at your functional scan, you should be able to, oh, what's happening there? Oh, is there just one volume here? Oh, wait, I made a mistake. Oh, here we go. Yeah, so if you click on the rest mask, so you highlight it, and then you can scroll through the volumes here. And you'll notice that there are many, what we call volumes or images as you scroll through. And you can even use this little button here and play a movie. And you can see sort of fuzzy stuff happening here. So that's the main difference between functional and structural images, or when you look at them. And that's why we call them structural images, because you can see the structure very clearly. And the functional images, again, are going to be these more blurry images here. All right, everybody able to see those? Any questions about anything? Anybody in the chat? Oh, wait, people talking in the chat? I don't know where the chat is. Anybody see any questions in the chat? You can just call them out. Okay. So again, functional MRI, it's looking at oxygenated blood flow. And what happens in the functional MRI and in the structural MRI is we break up the brain into what are called voxels. So think of this like a giant Rubik's Cube, but instead of 3 by 3, we have something like 50 by 50 by 50 or 50 by 60 by 90 or something. So if you look at this image here, each square that you click is going to give you a coordinate system. So you see coordinates here in MNI, coordinates here in voxel location. People tend to use MNI coordinates. So if you see in papers when they have XYZ coordinates, that's how they are getting the location of the brain there, using these MNI coordinates here, XYZ, and that will tell you the specific place of each voxel. And again, you can do this because MNI template is standardized. So whenever someone says, oh, voxel 1132, 35, everybody knows exactly where that is. Okay. What happens in a functional image? Well, here, each voxel records spatial location. So that's what this was. And in a functional image, essentially what's happening is that we are acquiring an image of the brain every 1 or 2 seconds. And that's what each of these volumes are. So each of these volumes is a 3D image of the brain, and each of these voxels will have a value. And another thing that's important to know is that when we acquire one of these so-called Rubik's Cubes, it's not acquired at one time. It's acquired in what are called slices. So essentially, you can break up the brain into 10, 15, 20 slices, and each slice will take about 30 milliseconds or so to acquire. So add those all up, you get about 1 image of the brain every 2 seconds or so. Now what they have are multi-band acquisitions. And essentially in multi-band acquisitions, you can collect 4 slices across the brain at once. So that's why you see now acquisition times of sub 1 second. And this slice acquisition is important because it leads to a couple issues in our processing stream. We won't talk about them so much today, but they're important to be aware of. One is that the timing of the blood flow in this area of the brain will be slightly disjointed from the blood flow acquired in a different area of the brain, right? Because it's about 1 second or 1.5 seconds behind. Some people don't think this is so much of a problem. Other people try to correct for it with what is called slice timing, and we'll be talking about that in the next session. But that's basically correcting for the offset in how they acquire these slices here. When you look at the image like this, it doesn't have any slice time information in it. It's just assuming everything was acquired at once. So that's why people try to correct it before you do anything, so you can shift the time series or the backwards essentially and try to line them all up. Nowadays, people don't do it so much. It does buy you some statistical power, but you have to be careful because when you look at the programs, it just has a button for slice timing, but your acquisition has to be set up exactly the way the program assumes you acquire something. So you can't just click slice timing and think it's going to correct it, because the program needs to know exactly how you got the slices and exactly what way to put them back together. And the odds that you acquire the data in the exact way the program or GUI is coded is not too high. So for that reason, we tend not to do it. And when we talk about especially in multiband, it doesn't seem to be necessary because the gap between the first and last slices is only like half a second or a second. But that's the issue of slice timing. Another issue is head motion. We're not going to talk about head motion today, but head motion occurs because of the way we acquire these slices. So if you remember again, the protons are spinning, we're shooting a pulse at it, knocking those protons over and measuring the resonant frequency after we hit that pulse. But if you move your head, the same slice of the brain is going to hit with that pulse twice. So it's going to artificially inflate the signal or deflate, increase or decrease the signal at certain points. So that's a big problem with head motion. We're not going to talk so much about that, but that comes from the way that we acquire the data again, because we acquire it in slices with this radio frequency pulse. If you move your head, a slice that has already been hit with a pulse will get hit again. And then that will cause you problems in measuring the resonant frequency because it's not the true resonant frequency. So these are influences of head motion on the bold signal. And if you go to this image right here, we can take a look at the time series. There's a way to do it. So if you go to view and then time series, it will show you the time series at that particular voxel for the entire scan. So this is what the bold signal looks like essentially. And then you can just move around the brain and see the time series for different parts of the brain. All right, any questions? Well, yes.
Do motion correction methods help with the problem that you just described?
The increase or decrease in the bold signal?
Yeah.
Yeah. But that's like a whole seminar in itself. But there's ways to mitigate that. But yeah, we could discuss that for a long time. But we can talk about that later, but there are ways to mitigate that. Yeah, but we won't get so much into that today. There is another type of motion correction you're going to see in the next FSL tutorial, and that's not quite the same thing. So that motion correction is, of course, when we acquire an image of the brain, sometimes they're going to move, right? So that type of motion correction is we're just putting all the brains lined up to one space. We'll talk more about that. But that is separate from the problem of them moving and the bold signal jumping. But that's a very good point. In resting state, that's pretty much what we're majorly concerned about, and you'll spend more time dealing with that than your actual analysis. Any other questions in the chat? Okay. So we're looking at some data that has already been relatively pre-processed. Again, I'm not going to go into this. We have videos. Those are the videos I sent out yesterday where we get a little more into some of these pre-processing steps for resting state. Today, later on, we're going to do going through some basic pre-processing for task fMRI. So the way you pre-process the data is going to be different for what you're trying to accomplish. And like I said, resting state is much more involved for this head motion reason. I'm not going to get into the details, but head motion isn't as much of a concern in task fMRI, just because of the way we analyze it. So we're just going to continue on here, assuming all this has been done. So again, I have those videos. Email me if you didn't get the links from yesterday. I'll find them and put them up. But we're just going to assume for today that all of that has been pre-processed, because that's what this image is. It has been pre-processed already. This is what we're going to talk about later on today, and I think it's important to understand this, to understand resting state also. So originally, people were interested in what areas of the brain are related to what process. So say you wanted to look at what area of the brain is related to faces, you'd design something like this: a face, a rest, a bunch of houses, rest, faces, rest. And the premise here is that an area of the brain that is responsive to faces will have blood flow like this. So what we do is we create this hypothetical ideal blood flow, which is this straight line. This is just for an example. You'll see an FSL that it actually gets convolved like a curve. But the assumption here is that an area of the brain responsive to faces will have a blood flow pattern, something like this. So this is supposed to be a hypothetical blood flow pattern here. And these square lines are our created ideal blood flow, which we will talk more about in FSL later. And then we're going to assume that if a part of the brain is responsive to houses, we're going to have a blood flow pattern like this. Okay. And if the blood flow pattern doesn't match either of them, we're going to assume the voxels isn't really involved in, or that area of the brain, which we call a voxel, isn't really involved in faces or houses. So what do you see when you essentially you try to match the blood flow through every voxel in the brain with this hypothetical or ideal blood flow square line? Again, this is just for presentation purposes. When you look at this in FSL, it's actually going to be curved because blood flow doesn't go in a square, obviously. But basically, you try to match this ideal blood flow pattern with the blood flow of every voxel in the brain. And then you see which voxels match this pattern closely. Essentially, there's a threshold. We'll talk about that later. But basically, that's how you're going to identify what voxels in the brain are responsive to what process or stimuli or whatnot. So you can just switch this and switch it with anything. You can put math or language, I don't know, executive functions, inhibition, working memory, whatever you want. So this is how people identify what area in the brain is responsive to what process. And this is what we'll be doing in the second part later on today. But basically, we are mapping our brain's blood flow to some external event, which is the main point. An external event which we are creating and which we are structuring in such a way that it allows us to identify which areas of the brain are involved in these structured events here. Okay, so this is the way fMRI was done for a long time. And then later on, a couple things happened. One was people started to say, hey, what if we look at these periods when we don't present the stimulus? And then another one was Barak Biswal had a paper where he showed areas in the motor cortex are correlated even though patients are doing nothing. And then this got people thinking, hey, maybe the brain doesn't have to be investigated in response to some external task. So instead of looking at blood flow patterns in response to external stimulus, or looking at these off periods, so-called off periods, what we can do now is instead look at blood flow in areas of the brain compared to other areas of the brain. So now instead of looking at blood flow compared to an external hypothetical regressor or something like that, we're just going to compare blood flow patterns between different parts of the brain to each other. And the assumption here is that areas in the brain in the same network are going to have similar blood flow patterns. So this is your posterior cingulate, medial prefrontal cortex of the default mode, or a network that's activated when you think internally. So autobiographical memory, self-referential processing, things like that. Your default mode is going to be activated. And you can see here that the blood flow of these red and yellow, or whatever these are, I'm colorblind, so excuse that. But these two lines right here, you see they're very similar. So if we correlated them together, we would get a very strong positive correlation. So the assumption here is blood flow is similar between two brain areas. We assume they're communicating and working within a network here. Now, if you look at the blood flow pattern in this parietal area here, if you're a parietal sulcus, you're going to notice these areas here, the blood flow is in opposition to these areas here. And these are areas involved in external attention. So anytime you're thinking outwardly, doing the task or whatnot. And you can see here, there's sort of this juxtaposition or anti-correlation, people call it. Essentially, when the blood flow increases in these areas, the blood flow decreases in these areas, and vice versa. You can see that throughout this scan here. And that's sort of what's happening here. So the external network comes online, then the internal network comes online, then the external, internal, external. It's not quite that simple, but that's basically the story there. So now we can look at the organization of the brain without any external reference. Now that we understand sort of how these different regions of the brain operate. And by comparing the blood flow patterns within each brain area to all other brain areas, we can essentially get a map of different networks here during resting state. So in absence of any task, these brain areas, which are the same color, tend to have similar patterns of blood flow, which are different from the other brain areas in different colors. And essentially the colors make up a particular network there. There's many different ways to divide this essentially, but that's the basic idea here. This is the parcellation that I had you guys pull off. So if we do, let's do file, well, overlay, remove all. And X out this time series also. So overlay, I did overlay, remove all, and then I just closed out that little time series box in the bottom. And if we go add from file, and we go to the parcellation. So the parcellations here, let's go to MNI. So they have different formats of the parcellation here related to different types of normalized brains, and I won't go into that, but that's what these are. So MNI, so this is the standard brain we're using, so this is the space we want to be in. And let's look at the 400 parcel, 17 network, 2 millimeter guy right there. So look for 400 parcels, 17 networks, FSL, MNI, this guy there, and open it up. Oh, is that tiny? That must be tiny. Sorry, that's as big as I can get it. Schaefer 2018, 400 parcels, 17 networks, FSL, MNI, 2 millimeter. So if we open this guy up, you'll see that it is this brain parcellation here from the image. And if you click on these areas, you'll see a number pop up here. So this is region of interest or ROI number 364. I can click over here. This is region of interest 371. And what that is going to match up with is if you open up the text file, they have included the README. Oh wait, it's not the README. Which one is? I have the coordinates here somewhere. Oh. All right, in one of these, oh, it's in the update. So you guys have this update folder? So if you go to these component number changes, oh, so I guess they labeled them wrong at one point, so they issued this update. But if you open this up, it's gonna give you the name or not the name, the network that each ROI is located in. So if you go over here, this one, ROI 371, the medial prefrontal cortex is going to be inside of network. What is this? Resolution. So 371. So 371, this part of the control network. So that's how you look at, or is that the old name? Yeah. So you can use the ROIs here, see what networks they're in, essentially. And then if you scroll around, that's how you can find a particular ROI. So if you're interested in a particular place in the brain, you can get the atlas, look up what number it is, and then we're going to extract the time series in just a little bit here. Okay, so what we're going to do right now is we're going to extract some time series, and then we're going to make them into a correlation matrix. And basically what happens is when you extract the time series for all these ROIs, you just correlate each one with each other. You're going to see a matrix like this. I'm sure you guys have seen these before. And this is basically the functional connectivity strength between each pair of ROIs. And what you're looking for is sort of this diagonal of stronger connectivities within networks here. So this is a default with the default, and we expect those areas to have stronger connections. So this is just a simple 2 ROI or 4 ROI by 4 ROI, and brain areas within the same network should be strongly correlated. So you're going to have red or hotter colors. Same thing with network 2 and network 2. So they should be strongly correlated. And then you're going to see brain areas between different networks should have no correlations or negative correlations. So the cooler colors here. And that's what you're going to see inside of these connectivity matrices. So warmer colors on the diagonal, and then cooler colors on the off diagonal, showing sort of the functional connectivity structure of the brain, the average structure of the brain. And this is the same thing you see in macaque monkeys, and then even in tadpole neurons firing. So this is a basic organization of the brain. And right now we will create a matrix like this. So the first thing we're going to do is we're going to extract some time series. You have your terminal here. Close out the FSL, close out the FSL eyes. Let's get our terminal going. And the first thing we're going to do is this command called FSL mean TS. So if you type in FSL mean TS, you should get these bunch of instructions show up. And for any command basically you're using from these programs, typically if you type in the command, just like this, it'll show you how to use it. And the thing for these is many different people have coded different parts of these GUIs. So the format of these commands are going to change according to which command you use. So it's always a good idea to look up the specific one you're using so you can follow the format. Sometimes they require these inputs flags, sometimes they don't. For this particular one, the format of this command here is FSL mean TS. Let's do another terminal. So the format here is FSL mean TS. And the flag here is the input, so -I. And then this is your input data here. So we are going to input the data from this one image normalized. So if you go to this data that I had you download, what we want to do is follow these inputs. We're going to FSL mean TS. The input file, you can look what these input 4D image. So the -I input your 4D image. And what you can do is just drag this right here, and it should give you the pathway to that file. So if you just drag the file here, it's going to give you the pathway, or you can type the pathway in. Okay. And now it's going to ask us to put, where do we want the output? Where do we want these time series to go? So -O. And then I'm going to put it right back into here. So we just change this to be .txt. Just get this for now. So we want the output. I'm just lazy, so I just drag that file name in here. We can call it anything. You can call it anything you want. Schaefer parcellation, Schaefer.text. I don't know, maybe you're doing a bunch of these, so you want to label it Schaefer 400. Let's just do a test, just to keep it simple. But that's all I did there. I'm just making a pathway now for where I want the output file to be. And I'm just saying, hey, put it back in this one, and we're going to call it test.txt. And now the last one is this -M or my mask option. And you can use a single ROI, and that's going to be the -M. So they call us a mask. It's basically, you have a bunch of voxels in the brain, and you say, hey, I just want this one area. Take out, get me the average time series for this one area. What we're going to do is we have these handy little things called label files. And that's what this Schaefer parcellation is essentially. So using a label file as an input, it's going to give us the time series for each one of those ROIs. So we don't have to do 400 individual commands here. So for this label file, the command is a little bit different. So if you want to use the label flag here, instead of the mask, we need to do -- label. Okay. And then we need to do equals to. So there's some quirks here whenever you use these codes. Okay, and the label file we want to drag in there is the parcellation again, MNI. Schaefer 200, or I'm sorry, Schaefer 400. Here. Okay, and that's our label file. Okay, so again, we're just following the setup of this. FSL mean TS. First flag is our input, -I. So I just put the pathway to the flag onto the file, the Nifty file. Now we want to extract the time series of output, where I want the output text file to go over the times, what the time series are. And then what mask or what ROIs do I want it to extract? And from this, I put in that Schaefer parcellation file. So the one we were looking at with the 400 ROIs. If you put all that in and press enter, you should get a file that is spit out. into here. Do that, and then now you have this test.text, which has the time series for each ROI, and we'll open this in Matlab just a bit. You don't want to work with these text files because this is just a mess. When we open it into Matlab, it'll format it nicely for us. Okay, any questions about that one? Is everybody able to get that file out? Anybody on chat? Okay. Make our, you can, I'm not sure how to do that. That's kind of hard, but I'm sure there's instructions somewhere to make your own label file. But the good thing is, essentially every major parcellation out there has a label file. So the Schaefer parcellations, Gordon parcellation, Power, maybe Power doesn't have it, but the Glasser parcellation, essentially every major parcellation should have a label file you can just download. If not, you can just get the individual ROIs and code a for loop, and we'll see that in just a second. So if you do have like 100 ROIs you want to extract, we can put this into a loop and extract it without having to run that command ourselves 100 times. Any other questions? Okay, so let's take a look at a for loop. So inside of the scripts folder, if you go to the Google, what do you call it? The Google Doc, there's a link. And I have this script set up. Well, we can start one from scratch. So what you want to do is open up your text editor. Let's do new. So you have your text editor here, and what you want to do is put this, oops, what's going on? $. Oh, there we go. Okay, you want to put this $, $, bin, dash. Okay, so you're going to tell your text editor to essentially locate this inside of your terminal, and it will read it as a script if you do a couple things. First thing is, let's see, we need to change this to plain text. So you cannot write a script using rich text. For some reason, it gets all screwed up. So if you have a text editor and it's in rich text, we want to format it, make plain text. And then let's just save this to a file, just save it inside the scripts. We'll call this just test. And you have to label it SH. So that's the other thing here. Okay, so now we have this test SH. And now what we need to do is make this work with Linux. So in order to do that, we wanted this chmod u plus x. So we have to make this script executable. So you do a chmod u plus x, you drag your script in there to this name here. And if you press enter, it's now going to allow this script to work with your terminal. And we can test if this works by just writing a simple code. Variable equals hello. Echo bar. Oh, absolutely. Sorry about that. Okay, so to do that, let's see if I did this correctly. And then what you should be able to do is drag your script in, and then it should print out hello. Okay, so now we have an executable Linux script where we can type in anything we want. And if you want to run it, you just have to drag it into your terminal again, and it's going to run it and hello. Okay. So, oh, and these things are very finicky. So if I put a space right here, it's not going to work. So you see, gives me an error. So Linux is very finicky. The other thing is switching between text editors is tricky sometimes, because sometimes if the format or the font of one of these changes, your code's not going to work. So it's always good to type them into the terminal if you're finding you have problems or whatnot. Because even though your code is exactly correct, if the font is not correct, Linux is not going to recognize it. Okay, so now we have this very simple bash script that we can edit. And we're going to do a for loop here. So if you open up this FSL mean TS script, I already have a for loop written. So we will go through it real quick. And we're going to put it into our terminal. So the first thing we're going to do is we'll just write this for loop in the terminal. Because it has to be formatted a certain way when you do a for loop. So I like to put it in the terminal because you don't have to worry about the formatting. And then what you can do is after you put it into the terminal, you can recall it just by using. So if you do your up arrow on the terminal, it'll bring up every previous command for the past few hundred or so. So if you ever do something and you forgot it, you can just go back through and look for it. Or you can also put history. And history will bring up your last few hundred commands or so. So you can always look at what your previous commands were and then save them. So in neuroimaging, we're going to do a for loop. And if you can do a for loop, you can pretty much do anything in neuroimaging. It's the foundation for most of the stuff we do. And what a for loop does is it says, for this list, do these commands essentially. So for all the files in this folder, do this process. For all the directories, do X. And in Linux, it takes a different form in Linux and in Matlab, but it's the same logical flow, I should say. But the language is slightly different. For Linux, the way you do a for loop is you're going to start for. And then we want to create some variable or name some variable that will encompass all the files in our list. So I called it here directory. You can call it folder. You can call it whatever you want, as long as you keep it consistent. And then what we want to do is we want to tell it. And structure is important. So when you see neuroimaging data, it's always set up like this, simply or mostly for coding, because you need a consistent structure so your code can just go through your file directories one by one, essentially. So you don't want them named different things, for example, because that's going to be harder to code, essentially. So for this, we just have a very simple in our side of our folder. We just wanted to go through all folders in here. So we could have 100 subjects, we could have 1,000 subjects. It's not going to matter. The code is going to be the same. We're telling it for all folders in here. So if we just drag this pathway, and the way we tell it to grab all the folders is to use this star, which is essentially a wildcard. So this star means anything inside of here starting with an S, it's gonna grab. So that's gonna be our variable folder. Okay. For this list called folder, that is consisting of every directory starting with S in here. Then you press enter. Oh, oops, what happened? For, oh, sorry, I need it in. For folder in. Yeah, and remember, this can be anything for directory, for folder, for whatever you want. I'll just keep it directory. Sorry about that, just to make it consistent with this. So if you put in this first line again, for this variable directory, consisting of every folder starting with S here. Okay, it's going to give you this little $sign. We want it to do our FSL mean TS command. Okay, so this is the setup here. For dir in every folder starting with S, we want it to do this FSL mean TS command. And we want it to do, so we have to fill out the rest of this now. So again, if you remember, our command is the inputs. Now the input is going to be this variable directory. So if you call it, it's $sign. So now we're calling it. And within each directory, we want it to pick up this rest mass file. So rest mask. Okay. So now this allows it to say, okay, subject one, this whole pathway is subject one dash rest, subject two dash rest. So that's why it's important to set these up in a similar format here. So I'll just delete these rest. You can see this code working. Okay, so now the output, we want to put it back into the same place. So back into that directory, and we'll just call it test.txt. Okay, and now we want to put our label file again. So label equals, and then just drag that parcellation again into there. So our shape for 417 networks. That is our label file again. And then if you press enter, it's going to give you another arrow here. And then you press type in done. And then this is a for loop. So it's going to go through every folder starting with S. It's going to do this FSL mean TS command. It's going to take this rest fast as an input. It's going to put it back into the same place, call it text.txt, and it's going to use the Schaefer label file for each one of these. Okay, so if you press enter, you're going to see these files now pop up. Okay, let me get that. And then you're going to get that. Okay. So simple for loop in Linux. And what you can do now is if you press up, you get the command there and you can copy this and put that into your script or whatever. Okay. So if you want to do anything else, essentially you just replace this middle part with whatever command you want it to do. Mask this file, duplicate this file, whatever you want, you can put in the for loop. And then as you progress, you put for loops in for loops. So you can say, for all the folders in here, we want it to go through 100 ROIs or whatever. So you put a for loop in a for loop, and then it basically does everything for you. So everything is set up using for loops pretty much, neural imaging. So if you can do a couple for loops, you can do a lot of stuff. All right, any questions on the for loops? Is anybody able to get a for loop running? No? Okay. Any questions in the chat? People are able to get a for loop running. I'm gonna assume that happened. Okay, and we're gonna do our final part now. We're gonna go into Matlab and create a correlation matrix. Oops. So let's bring up Matlab. Okay, so you open up Matlab. What you want to do is add SPM to your path. So if you go home, set path. Oh, is this tiny again? I don't know how to make this larger on this map. So it's home. Sorry, we can't see this. And then set path here. And then add with subfolders. And then you just want to add the SPM folder. I'm not sure how it works on the Hoffman. I think you have to do something a little different. Is anybody on Hoffman right now? No? Okay, we don't have to worry about it then. Okay, so you add your SPM here, and hopefully it works. So just add it as the path. Again, add with subfolders. If you close, don't need to save it. And you type SPM, you should get the GUI. If you're getting an error, like the MEX file error, you want to look at, I have it on here, the MEX file error. Is anybody getting a MEX file error? No?
I tried to, what is it called, compile it, I did get that error, but I was still able to open Matlab and SPM when I didn't bother to compile.
You got it though?
Yeah.
Okay. So I have a thing on here also, if you look about this MATLAB MEX file error. So again, updates. This is why we hate updates. Okay. So you can go here, there's a little code you can run in your Linux terminal that will get rid of that MEX file error in there. But if you are able to open SPM, did this open up? Should have opened up somewhere. Okay. So are you able to get the GUI though? People able to get the GUI? No? Hopefully. All right. So you may need to get some setup, but as long as you get the GUI to open, then that's what we need. We're not going to actually use the GUI, but this is how you know that it's working and you don't have an error or whatnot. So as long as you're able to open that, what we're going to do now is if you open the script I sent, or the one you download called the Create Core Matrix, open that in MATLAB. So you should be able to open that, and then it'll open up into this window here. You guys able to open up the script? Yeah. Okay, so we have some stuff in here. We're not going to go into this top part right now. The first thing I want to show you guys is just basically how to open a Nifty file. So what you want to do is if you have this script open, go to the fun image normalized, go to one of these. Okay. So in our fun image normalized subject 1, we have this rest masked file. And the first thing we're going to do is this gun zip command. So SPM does not like zip files. We have to unzip it. So just drag this gun zip command down here. We're going to do these one at a time. So if you just drag this gun zip, oh, whoops. Yeah. It should now give you this rest mask dot NII file here. Okay. And after you do that, what you can do is drag these commands now. So this V to ABCDY, this part right here, and drag this down. Just do this by itself. And if you do that and you have SPM hooked up correctly, it's going to open this Nifty file and put it into a matrix. Okay, so you should get something like this. So again, it's this part. Oops. Oh. All right. People able to get this part? Yeah. So if you get this part, this is essentially the information in the Nifty file. It tells you that it's 91 voxels by 109 voxels by 91 voxels large. So that's sort of our bounding box. And the bounding box is bigger than the brain. So you have to remember that. Most of these voxels are going to be blank or noise or empty space. So if we look at FSL eyes again, if you open up FSL, and if we open up that file again, let's see, desktop, just open up the fun image normalized subject 1 again. Oh, wait, I don't know if FSL likes this. Oh, okay, let's open it. Sometimes FSL doesn't like it when you have a zip file and a non-zip file in there. So you might run into an error later on when you do that, but I guess it's okay for the viewer. So the bounding box includes all these voxels out here. So you can see they're zeroed out. That's just because we put a mask. But in any data you acquire, there'll be values in here of just scatter noise essentially. So the bounding box is everything around here, probably like 200,000 voxels, but only about 90,000 so are actually related to the brain. So that is the dimensions here. There are 177 time points or images. And what happened was we took each voxel and made it into a 2x2 matrix essentially. So 177 time points by these 902,000 lines of voxels. But again, remember, pretty much most of these are empty. There's only going to be a few of them, or 100,000 of them or so that are related to our brain here. So if you look at this XYZ, this is going to give you the coordinates for each voxel here. So voxel 1 is located at -90 or 90, -126, and -72. So put them into here, 90, -126, negative 72. Okay, so you see this voxel is way out here in no man's land, so it's empty. So it's the first voxel right here in the corner. So if we actually look at a voxel with some signal, I'm not going to go through the trouble of finding it, but this is how you relate each voxel to each time series in Matlab. Right there. And then what you can do is say, if you want voxel 33 at this coordinate, you just go into Y and you get line number 33, which is going to be empty here. Okay, so if you want to plot one of these, all you have to do is, let's find some numbers first. So all I have to do is type in plot. The array is Y. We want it to get row 281113. Okay. And then we're gonna plot that row right there. So we just do plot, left parenthesis, the array we want to plot, which is Y. The row or voxel we want to plot, comma, we just want to plot against all the columns. So that's why it's this. And then a couple parentheses right there. So you can plot any time series you want to look at it. And what's going to happen is if we look at 28113, 28113, 2811113. Okay, so 64, negative 52, negative 60. 64, negative 52, negative 60. Okay. And if we do the time series, should get the exact same thing. Okay, so that's how you can get any time series from any voxel from your Nifty into Matlab. Okay, so that's the organization of your Nifty files. Now you can open it up. So that's if you want to get any individual time series you want. Any questions about the structure of Nifty files and how to open them? Okay, so last thing we're going to do is make our correlation matrices. Any questions from the chat? No? Okay. So what I want to do is just comment this out. I don't really need that. So we go to the editor. These percentage signs means ignore it. So we're just going to ignore those for now. So again, this comment, you can take away the comments. But you want to put this. So it's not going to read this part of the code. It's just going to say ignore it. And now what we're going to do is we're going to make the correlation matrix using these time series that we just extracted. Let's see. Okay, so the first thing we want to do is load this matrix into Matlab. Oh, let's go clear first. Clear our window. So just type clear into your command line. You can press enter. And what we're going to do is load this text. We'll call it variable A. So A is equal to load. And then just put it in here. So some variable we want it to be consisting of this text file here. If you press enter, it should load it up nicely for you. So now we have this 177 by 400 matrix. So again, we have 177 time points and 400 ROIs. So basically, each one of these columns now is time series for an ROI. So previously, the rows were time series, but now the columns are time series. So you always have to watch with these matrices. Otherwise, you're going to be analyzing nonsense. So here, if you want to plot, we can plot text. What is this? Row 1 now. Okay. So this is saying plot row 1, not the columns. So we want to take all the columns in row 1. Oh, yeah, there's something open. Oh, it's here. Okay. So let's do that again. Okay, so this is the time series for ROI1 inside of the Schaefer parcellation. Okay. Now, if you want to get the correlation matrix of this, it's pretty simple. All you're going to do is matrix, we'll just call this new one matrix, equal to the correlation coefficient of this matrix text. Okay, so make a new array, I guess, or vectors called matrix. And what we want it to do is just get the correlation coefficients between every column of this text thing here. And if you do that, it's going to give you a matrix. So this is your correlation matrix. And if you type in images C matrix, it's going to give you a nice little plot of the correlation matrix here. Okay. So this is an individual subject. It's going to be noisier, of course, in a group level analysis, but you can see along the diagonals, we are starting to get those within subject correlations. I mean, within network correlations. Here we have some between network connectivity, but basically this is your resting state correlation matrix. And as you average across the group, you'll get that stronger diagonal sort of formation I was showing you guys earlier here. Okay. So this is the individual subject level. As you get to the group level, you're going to get this stronger diagonal pattern here. And you're going to see a lot of individual differences on the individual subject level. And that's thought to be beneficial for resting state. So the more variability you have in these matrices, the more chances you have to identify individual differences related to these large differences. Okay, any questions on how to get the correlation matrix? Okay, so last thing we're going to do, anybody in chat? All right, last thing we're going to do is do a for loop in Matlab, so we can get the correlation matrix of each subject. I have this add gen path. So instead of doing your set path, you can put this little piece of code here. So it will add SPM to your path. You don't have to go through that thing up here. You can just put in this code, add path, put the path with SPM. I'm telling it to change directory. It's always a good idea to put this even in your Linux codes. Change directory to what directory you want to work in. So Matlab and Linux will put the outputs sort of in whatever directory your browser is in. So it's always good to change into that directory so you make sure your files are saved in that directory essentially, instead of saved in some random place where your browser is or your terminal line is. So inside of Matlab, the way we set up a for loop is first we need to make the list. So in Matlab, we're making this list called files. And it's going to consist of the directory of all folders starting with S. So you see it's a slightly different format, but essentially we're telling it just to make a list of all folders starting with S here. So if you put this into your command line and press enter, you should get a list of 2 files. So subject 1, subject 2. And now our for loop is going to say for this variable I, that's going to go up to the length of files. So in this case, it's 2. So it's just going to go for I equals 1 to 2. If we had 100 files, this would be 100 by 1 structure, and it would be for I equals 1 through 100. Okay, so it's saying go through every possible column, no row, go through every row, I1, I2, however many files it's collecting. And for each file name, the first thing we want to do is CD into this folder. So if I equals 1, it's going to CD into files 1.name. If I equals 2, it's going to CD into files 2.name. And then once we CD into that folder, we're going to want it to load our data. So what is our load command again? So we'll go TS instead of A equals load the text file. Okay, so make this array called TS or time series and make it from loading this text file. So we can just clear this, and then if you want to just make sure it works. Okay, so we'll do this. Oh, and if you put a semicolon here, it won't show you the numbers, so it'll speed up your processing. So that's why the semicolons are there. It'll just do the process without putting the output into this window. When you're doing massive amounts of data, you don't want it to waste time displaying all these numbers here. So TS load equals text. Now we want it to do make this matrix. So matrix equals the correlation coefficient of this TS. Right. So we can just put this on now. Put this into the editor. So now we have this matrix again. We want it to make a figure or put a new figure in the window. So that's the figure command. We want to see the image side of that figure. So that's the new one. Oh, here, let me put comments on it. Figure window. What's this? View matrix, correlation matrix. And then we can just tell it save this 4x4 matrix for us later. So that's what this save is. So save left parenthesis, save it as matrix.mat, and save that matrix as matrix.mat. Oh, we don't need this delete. Oh, well, you can delete the .nf. You only want one of these in here at all times. So I'll just delete the zip file we made. Okay, and then if you have this, we should have a simple script. I'll just take this out. run this. You can just add path when you run it. And it's going to spit out our matrices. And then also save our correlation matrices inside of each folder there. Okay, so this is the final script. I'll put it in the chat. Oh, sorry, I missed this question. If we want a specific time range, how do we note that? Yes, that is correct, Sabrina. Okay, was everybody able to read that script? Kind of. Really? Any questions? That's going to be the last thing we do right now. I think that's a lot. You can go around and go inside Matlab and play around with it. And again, basic format for the script, we can tell it do a bunch of other stuff. For example, we could tell it z-score the matrix first. So TS equals z-score TS. So z-score, and we're just changing it to standard deviations. So now if you do the TS, oops, yes. So I see it changes it to standard deviations. And you can plot the whole thing at once if you want to see outliers. So if you standardize it first, you can look at all the time series at once, and you see there's some kind of abnormal spike happening in the scan here. At this time point. So it helps to visualize it, to look at all of them. You can see these spikes, things like that. Okay, that'll be it. Do we have any questions? All right, thanks everyone. Just a reminder for the second session, if you go to the Google Doc, download the analyze data set. If you did not run to the tutorial, there's a new link on there. And Dr. Martin Monti will be here to run the second session. All right, thanks everyone.